This is a demonstration of the software that is shipped with all Vertilon photonic data acquisition systems. In this example, we're showing an IQSP582 system that's being used in conjunction with an SIB164A sensor interface board. The SIB164A is used specifically with the Hamamatsu H7546B. That PMT is a multi-anode photomultiplier tube that consists of an 8x8 array. This system is a 64-channel system, as you can see here, from 1 through 64. And what we're going to do is demonstrate a setup that was previously demonstrated in a video that you can also find on our website. In that demonstration, we have the H7546B PMT mounted on the SIB164A, and we use a blue pulsing light source to illuminate the array. So to get started, we need to configure several parameters that are relatively straightforward. What we do is we go to the system menu and we start with the data configuration. In this case, we have 16 channels in each bank already set up. There are 4 banks of data acquisition channels in an IQSP582 system. Since each bank consists of 16 channels right now, that means we'll collect all 64 channels. Our input polarity is set for positive, which is generally the convention used for the current that flows from a PMT. Since our data acquisition systems can also be used with silicon photomultipliers, sometimes it's necessary to set this input polarity to negative. The reason being that the current actually flows in the opposite direction in some of those devices. It depends on the biasing if it's positive or negative. But for this demonstration we use positive, and most PMTs will require positive. We have a data format that can be set, and you can use 17-bit sign magnitude, 16-bit 2's complement. This actually gives you a little bit more dynamic range with the systems, but this makes, by using 16-bit, the data packets that are produced by the instrument are more compact and easier to process. We have some other configurations called range bits, trigger and timestamp, boxcar width, front panel ADC. All of these are explained more in the manual. We actually have the timestamp turned on here. The timestamp has 100 nanosecond resolution. For longer acquisition periods, you could consider using possibly longer timestamp resolutions. So we go to the back here to the high voltage supplies, and even though the high voltage is actually set over here in the front panel, there's a configuration menu that shows up over here, which is really more or less a sort of a safety issue. Unless the front panel is configured by enabling this box here, you cannot turn on the high voltage accidentally through the front panel. So what we're going to do now is enable this section right here so we can turn it on and set a limit to the high voltage, which we'll use 250 volts here. The reason it's so low is because we're actually operating the PMT in a non-light tight enclosure for this experiment. So we're going to keep it so that there will be no damage to the PMT, but it will be high enough voltage so we can at least see some signal from our source. Okay, you'll notice now that this section is no longer grayed out, so we can turn on the high voltage if we wanted to, and we can adjust the high voltage to the 250 limit. For this particular PMT, you can go up to close to 1,000 volts, and if we wanted to, we can set things accordingly so we can get that far. Some other features you'll see in this graphical user interface is a trigger count, which keeps track of all the triggers that enter the system, a trigger rate, which is going to report the average trigger rate within this gate time period, which can be set between 1 and 10 seconds. So if you have a fast trigger, you'd set it to 1 second. If you have a really slow trigger, maybe something that's looking at cosmic rays, you might go as far as 10 seconds. This particular box keeps track of the events, the event count, And the events are different than the triggers, because not all triggers necessarily result in an event. Basically what happens is the system will acquire an event based on a trigger, and if another trigger comes along too quickly, the system will not be armed and not ready to accept an additional event, so that event will actually get missed. The system is quite fast. This particular system will run at about 200 kilohertz, 250 kilohertz even. So you can collect quite a bit of data, and you'd see this event count moving accordingly. There's also a front panel analog to digital converter whose value is being reported out here. And we also show the timestamps. This is just sort of a power on timestamp right now. Regarding the display, we have this section here. We can set it to bar graph, 64 or 32 channels. There's 32 channels. There happens to be no data there. This is showing channels 33 to 64. We can instead choose channels 1 through 32. And then we have some two-dimensional displays. Sometimes customers like to use 4x4 arrays of 16 channels each, and you can show them side by side, and you can even pick which set of channels you use. This is particularly applicable to maybe experiments involving PET, where coincidence detection is being measured. Another display mode is the 8x8, which is most appropriate for this particular demonstration. Once you set up the 8x8 display, you can transpose these axes and flip them so that you can have the display match the orientation of the PMT. Some other configuration information or configuration data we have here would be the integration period, which in this case we'll set to 2 microseconds. Generally you'd want this to match the width of your pulse of light that's coming in. We're going to use internal trigger mode, so it's just going to be a 1 kilohertz rate that's going to develop. Sometimes it's more appropriate to actually use external trigger. So if you have a randomly arriving particle, a trigger signal that originates on the SIB164A is plugged into the front panel of the IQSP582, and that signal is used to trigger the acquisition of the event. If you're using external mode, you could consider delaying the acquisition of the signal by some amount of time. This way you can position the integration period directly around the event that occurred. We also offer other modes of triggering, a level trigger, which is explained more in the manual, and an input trigger, and also a pre-trigger. And you can see here, the pre-trigger allows us to actually put in negative numbers here, so we can collect data that occurs just prior to the trigger signal. But as I had said earlier, for this example, what we'll do is we'll use the internal trigger mode, and we'll set it to 1 kilohertz. Once you have your sensor interface plugged in, sensor interface board plugged into the system, you can configure it using this button here. It opens up. It says the particular device, which is the H7546B, and we can set, in this case we're setting up a discriminator. So we can choose the preamp's gain, we can choose which type of discriminator, leading edge, constant fraction, or zero slope, and there's various parameters you could set for each type of discriminator that you choose. You can set a baseline adjustment and then a threshold adjustment, and then the output trigger signal you can set the polarity of, positive going or negative going. We do have LEDs on the sensor interface board, not just this SIB164A, but virtually all of the sensor interface boards we make. Sometimes it's convenient to have the LEDs enabled so you can see what's going on, but if you're worried about light leakage, you would turn those off. In this case, we're probably not going to use the discriminator, so we'll just turn it off. And we're going to use the internal triggering in the system. So if I now go here and set our voltage to 250 volts, and I'll set this bar graph to 64 channels, set this period to 2 microseconds. It changed because I went to the pre-trigger mode. And then I'm going to enable high voltage. And I'm going to start the acquisition. So you can see the noise in the system, just a low noise. And as I shine this pulsing blue light source, you can see the various channels being excited. It's more appropriate, of course, to display this particular array in the 8x8 mode. And you can see here pulse moving around on the array. If I increase this integration time a little bit, maybe to 4 microseconds, you can see things are a little bit brighter. You notice the trigger count is increasing. The trigger rate is about 1 kilohertz. Which you see here. The gate time is set to 1 second. And it's counting events. You can also see the time, or the timestamp running here. So if I stop this acquisition for a second, and it's just a little easier to show, there's actually data flowing when we're in this mode, although you could see the data changing in this mode if you decrease the sensitivity here. You can see, you can adjust the gain there. Just go back to this mode, you can see the data flowing. If I stop the acquisition, the display freezes and no more data is being displayed. So we have various modes here for acquisition. The display mode is useful for diagnostics and for just setup of the system. When you're actually ready to acquire data, the display will shut down and data will be logged continuously to a file. So if we were to, let's say, select maybe particle or image mode, both of these are high-speed acquisition modes, and they're explained in more detail in the manual, but let's just take this image mode. We can set up, let's say, we'll take 10,000 triggers at 1 kilohertz, right? And make sure everything's set up. The high voltage is still on. So now if I press this button, it's going to ask for a file name. I'm going to call it photonic.log. I say OK. I'm just going to replace this because it already exists. And it's collecting data. So it's going to collect for 10 seconds and collect 10,000 events. 10,000 triggers, sorry. And this data could be played back using this playback mode. And the way we do that is we go to this thing called log file viewer. We press file select. Look for that file. This one here. Okay. We collected 9,995 events there. And when we play it back, you can see the data coming back. In this case, it was just noise. If I happen to have, here I'm indexing through different events in the file. If I happen to have a signal showing, you would see the signal actually responding here. So if we go back to display mode, if we want to acquire, let's say at a very high speed, let's say 200,000 hertz, we're going to make our trigger end count, let's say 500,000 triggers. So that'll be 2.5 seconds. Okay, I'm going to go back to image mode. I'm going to give it the same file name, so we'll override it. And we're going to replace it. So it's going to count for 2.5 seconds. You can see it's counted its 500,000 triggers, and it took all the data. Missed a few events because it was going so fast, and this data is arriving randomly. And it stores it in a file. So if we then come back and play back that file, what you see here, oops, mistake there, let's go back to display only, like that. And if we play back that file, I actually was running the pulse source at the time. So you can hit play. It's a pretty bright signal. And you could actually see the pulsing action of the pulse source, because the trigger rate is so high and the pulse is actually longer than the 4 microseconds.